right, so what if we took that $1,000 and wanted to know what our future value was in 2 years? Well, if we had an interest rate of 7%, this is how we should set this up, right? So we should set up a number line, right? So just a straight line with ticks for 0, 1, and 2. So those are all the years that we're dealing with. And we could say, well, what's happening is if we draw a line from 0 to 1 is, well, in year 1, we're going to compound that interest. And it's going to be the same as we saw in the simple interest case. It's just going to be 1,000 times 1.07. Okay? But what's going to happen is when we're compounding, we're including that interest on our next compounding calculation. And so we're going to have this amount of 1,000 times 1.07, and this whole thing is also going to be multiplied by 1.07. Okay, so let's gonna see that in action. So that first point, 1,000 times 1.07, that's going to come out to be 1,070. Okay, so that's going to be our first year. Now the second year, we're going to have the whole thing multiplied again by 1.07. And notice that if we're going to multiply something by 1.07 and then by 1.07, we could just square the term. Okay, so in our particular case, we have 1,000 times 1.07 squared, and that will give us $1,144.90, which is $4.90 more than we would have if we were doing simple interest. Okay, so in general, you may have noticed that the exponent was the number of periods we were going in the future when we're calculating the future value. And in fact, that's exactly what's going on. So our general formula for calculating the future value is just going to be our principal amount in times 0 times 1 plus the interest rate raised to the power of the number of periods that we're going in the future to. Okay, so let's do another example, this time with the story. So we've got Julie Miller. She wants to know how large her deposit of $10,000 is today. So she's going to deposit $10,000 in the bank today. And she wants to know in 5 years if she has an interest rate of 10% compounded annually and continuous and not continuously but compounded each year. How much is that investment going to be worth? Well, it's going to be the same thing here. We're going to start out with this $10,000, and if she went one period in the future, she would have 10,000 times 1.1. But then that amount, that 10,000 times 1.1, would be multiplied by 1.1 for the second year. Okay, so it'd be 10,000 times 1.1 squared. And that would happen again and again and again. Okay, so what she would end up then is 10,000 times 1.1 to the 5th power. Okay, so if we multiplied that out, we would have 16,105.10. Okay, so that's really all there is on using this compound interest to find a future value. Okay, so let's do a little bit of an aside here. If we wanted to find out how quickly we could double some amount, and we're talking about money here, but we could be talking about other things. In fact, I think in the homework, you're going to see some questions where we're doubling things other than money. Okay, so if we just wanted to quickly figure out how long it would take to double an amount of money at a given interest rate, we could use what's called the rule of 72. And 72 is a bit of a misnomer. Most of the time we use 72, but sometimes you might see in a question use rule of 70 instead. And that's just to make the calculation a little bit easier when we do that. Really, this is all an approximation, right? And we're just going to try to make the numbers work for as well easy as we can. So if you see in the homework something called rule of 70, rule of 69, rule of 71, probably won't do rule of 71. That doesn't divide by much very easily. Then just use that number that I give you instead of 72. But our default's going to be just 72. Okay. So how do we use this number? Well, we could find the approximate years it's going to take to double, approximate number of periods it's going to take to double, if our interest rate is talking about some other period, by dividing 72, or whatever number we give you, by that rate. But when we're talking about the rate, we're talking about rate times 100. Okay, so we're going to divide 72 by 12. We're not going to divide 72 by 0.12, which is what 12% is. Okay, so if we divide 72 by 12, which is, we see that up here, that 12%. So if we divide 72 by 12, we would get about 6, right? Well, the actual amount it would take would be 6.12 years. So that is a pretty good approximations for something we can do in our head. So you can use that as a party trick if you want. But we'll definitely have some homework questions and exam questions that have some kind of creative ways to do this. So if you see rule of 72 in the question or rule of 70 in the question, then you can obviously know that this is what we want you to do, something that has to do with this. However, another key, in case we don't do that, is the fact that I may say approximately. Okay, so approximately is your key word to know. Use the rule of 72. Most of the time I want you to make an exact calculation. If I want you to do just an approximation, then use a good chance that I want you to do the rule of 72. All right, so we talked about the present value, we talked about the future value. Now let's talk about the present value, okay? So we've got some amount in the future, and we want to know how much is that worth now. So you can imagine this is going to be very similar to what we did with the future value problem. Future value problem, we had our amount that we were interested in. We multiplied that by 1 plus the interest rate raised to the power of the number of periods. Here, it's going to be very similar, except we're going in the opposite direction. So what are we going to do? Well, instead of multiplying by 1 plus the interest rate raised to the power of periods, we're going to raise to the power of n. We're going to divide instead. Okay, so in other words, this $1,000, we're going to discount it back one period, and that's going to be 1,000 over 1.07. Okay, but we're going to discount that amount back again, and we're going to have 1,000 divided by 1.07, and that is going to be divided by 1.07. Okay, in other words, it's going to be 1,000 divided by 1.07 squared. Okay, so we're going to the future, we're going to multiply, we're going to the present, we're going to divide. Okay, and so that's our general formula, what we just described. Okay, so let's do an example here. So we got our Julie Miller person again. She wants to know how much of a deposit she has to make now, such that her future value will be $10,000 in 5 years if there's an interest rate of 10%. Okay, so in other words, we've got this $10,000 in year 5. We want to discount it back this many times till we get to 0. Okay, so we're just going to take this $10,000 and we're going to divide by 1.1, and we're going 5 years, so we're going to raise it to the 5th power. Okay, all right, so if we do that, we should get $6,209.21. Okay, so that's pretty much it for finding the present values using compound interest. Now, we could have a different type of kind of revenue streams called annuities. And annuities are when we have a series of payments. So far we've only seen one payment. Either we're thinking about getting a payment in the future, or we're making a payment now and see how that accrues interest over time. But annuity represents multiple revenue streams over time. Okay, so for example, your student loan payments, car loan payments, you may pay insurance over time, mortgage, retirement. Okay, so all these things, rent at your apartment, really, that's not something that you're going to get to hold on to yourself, but your rent's not going to be changing over time. So it's a revenue stream for somebody, right? So parts of an annuity, well, today we're assuming we're not getting anything, but at the end of the first period, we're getting some amount. We're getting that amount again at some point later, and the same amount of time in between these, we get another amount. So in this case, we're doing them 1 year apart. So in each of these years, we're getting the same amount. Okay. So how in the world are we going to solve for the present value for this? Well, there's more than one way to do this, but we could just say, well, we're getting $100 in period 1. Let me discount that back to 1 period. We're getting some amount in period 2. Let me discount that back 2 periods. And we've seen how to do each of these things. So we could just, do whatever the nth period is, discount that all the way back. So discount all these different individual cash flows back to the present, and then add those amounts together. So that's one thing that we could do. Okay, so for this particular example, if we're going to get $1,000 every year for the first 3 years at a 7% interest, well, we just do our present value formula 3 different times. Okay, the first time we're discounting it back once, so we're going to have 1,000 divided by 1.07. Second period, we're going to discount $1,000, so we'll have 1,000 divided by 1.07 squared, and then third period, we're going to have 1,000 divided by 1.07 cubed. And we're going to figure out what all those amounts are, and then we would just add them together. Okay, so we could say, what is the value of this annuity? And that is $2,624.32. Okay, so some of these problems can be a little bit tricky. You're going to have to make sure that you read them very clearly. Okay, so for example, you should always draw a timeline. Okay, why? Because sometimes we might be asking, well, discount it from the 4th period to the 3rd period, right? And then do this, then do that. So if there's once these start to get a little complicated, making a timeline is going to really help you through that. You're going to have to make sure that you know whether or not it's present value or future value problem. So make sure you've kind of put in thought into that. Does it involve multiple cash flows? And once you figured out all this stuff, work towards solving it. Now there is this alternate formula for an annuity. I figure the amount of time that it takes to set this up, most of the time you may as well just calculate it as we do, because the more you kind of set in here, the bigger of a mistake you can probably possibly make. But if you do want to just use one formula instead of discounting back several cash flows, feel free to use this. You should get the same number. But I'm not going to stick on that for too much. I think we're not going to have a large number of periods to discount back. So I feel like the way we typically deal with them as we have in our examples is a little bit easier. Okay. Now this example is interesting because we have different amounts in different periods. Okay. So how do we deal with that? Well, we could deal with it in a couple of ways. We could just, first of all, we could just discount all these values back, just like we always do, right? Okay. Or we could use that annuity formula and just say, well, there's an annuity of $100 for 5 periods, okay, and then just plug that in. We could say there's an annuity for after that, there's a new, so we've taken care of $100 in each of these periods. So this is now 500 that we have to deal with. So this should be 300. Okay, and now we could say, well, there's an annuity of 300. So then we would plug the 300 into that formula. Okay, so then This would be 0 left. This would be 200. This would be that would still be 200. Right. So now we've got an annuity of 200 that we could deal with. So we could plug that in, or we could just discount them back. Okay. So there's more than one way we could do this. Okay. So so here's just an example of us just discounting each of these individual things back one at a time. And other than the chance of error, that's probably the easiest way to go, right? So yeah, that's probably how I would do it. All right, so we could do this, do some compounding more than once a year. So if that's the case, we would just alter our formula slightly. Okay, so we could have it such that we've got m being divided in this interest rate bit. So we got 1 plus I divided by m now instead of just 1 plus I, and then we would multiply in our exponent the number of periods, time in this case years, times the number of periods per year that it will compound. Okay, but this is just a more advanced version of that exact same formula we've been looking at. Okay, so how big of a deal does this make? Well, let's see. So Julie Miller has $1,000 to invest for 2 years at an interest rate of 12%. Okay, so if she was just getting annual compounding, she would get $12.54.40. If she was doing semi-annual, she would get $12.62.48. So she'd get more, and it's not that much more, but she'd get more. But let's see how much more if we keep increasing the number of times that she would get compounding. Say quarterly, so 4 times a year. Well, she'd get $12.66.77, monthly $12.69.73, and daily $12.71.20. Okay, so right now we've got it from daily of $12.71.20. And if it was annual, it would be $12.54.40. So we've got a decent amount of difference there.